All right, AP Calc, let's settle in here for section 9.3, and depending on the order in which we're doing things this year, this might just be the last section of notes that we're taking the entire year. So what we're doing in 9.3, in 9.1, we discussed what a differential equation was and how to solve it. But one of the things you have to learn anytime you're studying something, but especially in math or in science, is that there are certain problems you just can't solve. And approximating a solution is sometimes the best thing that you can do. Well, in differential equations, there are going to be certain diff-EQs that I'm not going to say necessarily they can't be solved, because frankly, this is beyond my scope of expertise. But there are certain differential equations we are not going to be able to solve this year with the methods that we're learning. Let's leave them at that. So we come up with two methods right here for approximating solutions to differential equations. One of which is called a graphical method right here, and the second of which is called a numerical method. So the first thing we're going to talk about, our first video here from 9.3, is going to introduce the concept of something called a slope field. And this is what we mean here, guys, by the first part, a graphical approximation method to a differential equation. And just to kind of introduce the topic, I went online here, guys, wow, apparently a long time ago, this was 2006, and found a wind map. And I thought I got this off the Weather Channel, but I don't know, it's off some sketchy website right here. So I'm not sure why, but I went to the Middle East right here and found a wind map. And what's going on here, guys, is that the arrows, as I think you could probably guess, are indicating measurements or readings that were taken at a weather station. So the direction of the arrows is telling you which direction the wind is blowing. And I thought maybe it would be the size or the length of the arrow, but actually, I think it's this color scale right down here that tells us the units right here, how many miles per hour our wind is blowing. So obviously, most of this map is in kind of this pink and purple and blue range. So it looks like most of our winds are over here, maybe between 0 miles an hour, and the biggest ones maybe get here to about 20. I guess if we ever saw some yellow or orange over here, that would mean really, really high winds. So a wind map tells you two things. It tells you what direction the wind is going, and it also kind of tells you how pronounced it is. Really, these are like vectors, which have direction and magnitude. So what would that tell you guys? If I were to tell you guys that a particular, I don't know, lightweight object like a plastic bag, or if we wanted to get more pronounced here and say, oh, I don't know, like a biological weapon with toxic gas was dropped in a certain area, we might be able to predict then where that poisonous gas, or maybe just that plastic bag, was going to go, just kind of following the arrows right here and seeing where the wind might take this. So that's one particular path right over there. Or maybe if we drop something over here in northern Iran, maybe our wind would take us over here somewhere and something like that. It gets a little bit weird at this spot, but maybe we would end up over there. What you wouldn't see, though, guys, is if you drop something here in Jordan, the thing just wouldn't travel like this. That doesn't make any sense, because that's totally against, or at least not in direction with, the direction of the wind. Okay, so that's how a wind map might be read, and a slope field is really something similar to that. So let's dive in and see what the heck we're talking about here. Now, a slope field, let me say again, is a way to graphically represent the solution to a differential equation. And sure enough, what have we been given right here? This is a differential equation. It's an equation in which the derivative of y has been given to us. And there will be certain differential equations that are going to be too complicated for us to solve. This isn't one of them, but I wanted to start you off with something easy. So let me show you guys how a slope field works. dy dx, obviously, is our derivative, but it also represents the slope of our tangent line to our particular function. And in this particular diff-EQ, this is probably the only one you're going to see like this, the derivative we have been given is a constant. It doesn't matter what the values of x and y are at any particular point, our derivative has a constant value of 1/2. Now, if you think about that, guys, if your slope is going to be constant, what kind of function are we talking about there? The answer, the solution to this differential equation has to be linear. But let's pretend we don't know that right now. Here's how a slope field works. At every point they give you on the graph, and I've given you a lot here. I've given you 1, 2, 3, 4, 5, 6, 7 going across, and 1, 2, 3, 4, 5 going down. We've got 35 points here on this graph. At every one of these 35 points, we're going to evaluate the derivative derivative that we've been given at the particular x and y coordinates of that point. However, this one's really simple because there is no x and y right here. Everything is constant. So no matter which point you're starting at, like if I started from this point right here, the slope of the solution curve here is equal to 1/2. So what I'm going to do is think about a slope of 1/2, which is up 1 and 2 to the right, and I'm just going to draw a small little line segment there, guys, that mimics that slope right there of 1/2. Now, the thing about this is, this particular slope, this derivative, is constant. So no matter what point I'm at, I'm going to get the exact same slope here of 1/2 at every one of these 35 points. Now, I'll tell you right now, on a quiz or a test or the AP test, you're not going to have to do this at 35 points. The ones on the AP test, usually about 12, is as many as they give you right here. This obviously gets a little bit tedious, but that, guys, is what your slope field looks like. No matter what point you're at, you drew a tiny little segment with a slope of 1/2. Now, that's it for drawing the slope field. Now, unfortunately, you guys have no idea at all what it is that we've accomplished. So I'm going to switch to green now, and I'm going to show you guys what it is that we've accomplished, but I want to be loud and clear. What I'm about to do in green is not something you have to do on your homework anyway, and depending on the directions, very likely not on the AP test either. What I'm going to do, guys, is actually separate my variables here and get dy is equal to a 1/2, and then I'll move the dx to the end here, and I'm going to actually go ahead and try to solve this differential equation, which I think I can do. Antiderivative of 1 with respect to y is y, and the antiderivative of 1/2 with respect to x is 1/2 x plus c. Now, that's as much as we can do. That is our general solution. And as I think you guys can tell, there's an infinite number of functions there that meet that format. But what do they all have in common? They are linear functions, like we thought we knew, with a slope of 1/2, and whatever that c value is, that's their y-intercept. So let me just draw one of them for you. Let me just say real quick, what if c was equal to -1? I'm just assuming now. Then -1 would be my y-intercept, and the slope of this linear function would be up 1, right 2, or down 1 and left 2. And I would draw the solution curve now that passes through those 3 collinear points. And the question I would ask you now, guys, going back to our wind map on the previous case, are we looking at something that makes sense, like this path right here, or are we looking at something that's just totally chaotic and not paying attention to the wind at all? Hopefully you realize that it's this first case here that we're actually looking at. That green line seems to fit pretty well within the slope field that we have drawn. Or, let me do this real quick. This is what it would have looked like if c was equal to 1. What would happen if, let's for example, c was positive 2? Now our y-intercept is 2, up 1, right 2, and I think that's all I really need to draw right here. That is what the solution curve would look like if c were equal to positive 1. I think I said 2 and meant 1 and drew 1, so let's just change that. There you go. So once again, that green solution curve seems to fit pretty well within the slope field. So if this differential equation were too complicated and we were not able to come up with the solution, we can at least come up with a graph, guys, a picture of what we think the solution curve looks like. Maybe it's this first one we did right here, maybe it's this second one we did right here, but it fits pretty well within the slope field. Now again, you guys, nothing I did in green was necessary in this problem. I'm just trying to explain to you guys what in the world it is that we're doing when we talk about a slope field and when we draw a slope field. But as I said, that was a pretty easy example because your derivative was constant. You won't always get so lucky. So let's take a look at a second case like this, where our differential equation, dy dx or y prime or f prime or whatever you want to call it, is equal to 1/4 times x. Now the plot thickens here, guys. Now, at these 35 points, to figure out the slope of the tangent, everybody, or the value of dy dx, you have to multiply the x-coordinate of whatever point you're at by this 1/4. And whatever you get for that product, that's the slope of the line segment that you're going to draw, a tiny little piece. Now, I told you guys just a second ago, you won't normally see problems where you've got to do slope fields at 35 points, but that is what I'm making you do here in our notes. But guys, here's the deal. You will find patterns pretty quickly that allow you to save a lot of time. For example, what would be the easiest x value to put in here to evaluate this derivative? How about x equals 0? Like, for example, at the origin right here, our x-coordinate is 0, and 1/4 times 0 is 0. So I draw a little horizontal piece right there with a slope of 0. And where else will that happen? Anywhere else that your x-coordinate is 0, like the point 0, 1, like the point 0, 2, and in fact anywhere on the y-axis. We're going to get a value right here of 0 for our derivative. Let me push now just a little bit to the right. Right here, x is 1, and 1/4 times 1 gets me a slope of 1/4. Now, I promise you guys, I'm not going to pull out my ruler and my protractor and make sure that your slope is exactly 1/4. The important thing is, guys, it's got a positive slope, but it's very shallow, not steep at all. And the same thing will happen at the point above it, when x is 1. The y-coordinates here are different, but the y-coordinates have no bearing in this particular diffie-q on the value of your derivative. So this graph is what we would say is consistent in columns. All right, everything at x equals 1 has a slope of 1/4. If we push to the right now, where x is 2, now it would be 1/4 times 2, so a slope of 1/2. Still positive, but a little bit steeper than it was just a second ago. And if I push just a little further to the right, where x is 3, now our slope is going to be 3/4. Still positive, but a little bit steeper than it was before. Now if I moved over to the left, into the, let me just say, left of the y-axis, where our x-coordinates are all negative, here our slopes are going to be negative 1/4. And I would love to see some symmetry here, guys, between this column and this column right here, because these slopes were all supposed to be positive 1/4. These, should have drawn that up there, these slopes should all have been negative 1/4. Let me move to the left a little further, where x is negative 2. Now these slopes should be negative 1/2, so negative but a little steeper. And all the way to the left now, that slope should be negative 3/4. Now I can tell right now I'm drawing these a little bit steeper than they probably should be, but it's the overall impression here, guys, that matters. All right, not the individual details. So that, you guys, is what our slope field looks like for this particular differential equation. And once more, I'm going to switch to green. You won't have to do this very often, guys, but let me just show you what's going on right here. Can we evaluate, or excuse me, can we solve this differential equation? And if so, does our solution fit well? I want you guys to look at that graph in purple and think for a second, what kind of function looks like it would fit well within that slope field? Another question is, if our derivative is what kind of function? This one here is linear. Then you might start thinking about what would the antiderivative of that function be. You might see where I'm going with this. Let me bring the dx to the other side. dy would equal 1/4 x dx. And we'll go ahead now and anti-differentiate both sides of this equation. We'll get a y on the left, and on the right, that x becomes an x squared. We divide the 1/4 by that 2 and get a 1/8 right there. Y is equal to 1/8 x squared plus c. Oh, now we're dealing with a quadratic solution to our linear differential equation. It's quadratic. It opens upward, and that 1/8 means that it's a pretty wide parabola. So for example, if c were equal to 0, we would probably just draw a nice, smooth, but wide opening parabola, maybe looking something like that. That's what would happen if your constant were 0. Or if c were negative 2, you'd probably draw the same shape right over here, but it would just start 2 units lower. And that's what it might look like if c were negative 2. And obviously we could do more of that, but I think at this point we're starting to get the feeling here, guys, the sense that, yeah, these solution curves fit nicely within the slope field. Okay, so A and B weren't too bad. A had a constant derivative. B had a derivative that was defined just in terms of x. And that meant that the y-coordinate was irrelevant. So all of these slopes were the same. And all of these slopes were the same. This is a graph we said would be consistent in columns. Maybe you can guess where I'm going next. Oh, wait, I lied. No, I outsmarted myself. Okay, this one, no such luck. We've got y and x involved in this one. So we're going to have to be a little bit more thoughtful, I think, about how we draw our 35 slopes. But again, there are always shortcuts. Like, for example, when you're taking y divided by x, the first thing I would notice right there is that if your denominator were equal to 0, then your derivative, dy dx, would be undefined. And what kind of line has an undefined slope? That, everybody, is a vertical line. So anywhere on this graph that your x-coordinate were equal to 0, you'd end up with an undefined derivative and a vertical tangent segment. So that would happen clearly at the origin. Sorry, that's hard to see there, guys. And anywhere else on the y-axis. Everywhere that x were equal to 0, which are these 5 points right here, you'd get a vertical piece right there. Now, what we really have here, guys, because this is the first time we've seen this, because all 5 of those segments are pointing directly at each other, what we really have right there, guys, is a vertical asymptote. We have a line right here that this function is probably not going to cross. Now, what's next? The tricky thing I want to write here is the following now. We already talked about what would happen if the denominator were equal to 0. But what if, everybody, the numerator were equal to 0. However, I got to be careful. If y is 0, but x were not equal to 0, okay, that's important. If we had 0 over some other number, then your derivative, dy dx, would equal 0, just like we saw a little bit of on the last problem, and that would give you a horizontal line segment. But again, guys, it's important to get this right. This happens, a horizontal line segment, anywhere on the x-axis where y is equal to 0 and x is not. So this does not happen at the origin. So this idea right here, guys, of the denominator equaling 0 and that giving you a vertical tangent segment, that has to happen first. That trumps the horizontal that you might get. So I'll warn you, that's something that your AP graders will be on the lookout for. Okay, this person knows what's going on, but did they get the right priority right there at 0? 0 divided by 0 is not 0, it's undefined, and that means we have to have a vertical tangent segment right there. So be on the lookout for that. Okay, so when I told you guys we would look for shortcuts, so this 35 maybe wouldn't take you quite as long as you thought, that's what I'm talking about. Look for spots first where your derivative is undefined and draw vertical tangent segments. Then look for spots after that where that derivative would be 0 and draw horizontal tangent segments. Here's another little kick, guys. If x were equal to y, again, assuming then that we're not talking about a spot where x is 0, then your derivative, dy dx, is going to equal 1. That happens right here at the point 1, 1, so a slope of 1, and the point 2, 2, and I'm not done yet. -1, -1, -2, -2. There we go. How about another rule? If x, that's not what I wanted to write. If x and y were opposites of each other, then dy dx would equal, that should have been a comma right there, would equal -1. And that happens at -1, 1, -2, 2, at 1, -1, and at 2, -2. So hopefully you guys are seeing my point right here. Yes, there's 35 little slopes that I have to draw, but it's not like I got to sit here and do a whole bunch of math 35 times. There's definitely some shortcuts. All right, after this, though, things get interesting, and I think I'm just going to dive in. Right over here, guys, at this point, I'll erase that in a second, at the point 1, 2. My 1 goes here, my 2 goes here, and I end up with a slope of 2. Now, you'll notice up 2, right 1, but also if I went down 2, left 1, that points me right back towards the origin. The same thing would happen right here, you guys. At the point -1, -2, the negatives would cancel. And I wonder if at this point you guys aren't starting to realize what's happening here. How about at the point right there, 2, 1? Now, I'd put a 2 in for x and a 1 in for y, and we get a slope of 1/2. Which again is pointing us right back towards the origin. And that would happen there. And I'll cut to the chase, guys. That happens at every single point on this graph. Your slope field always points right back towards the origin. This is kind of cool. And you get this really neat starburst looking pattern here that we have going on. So this is one of my favorite slope fields right here. I thought this one was really interesting. Basically, everything shoots out of the origin right there. Now, why is that? Once again, you don't need to write anything I'm about to do, but real quickly, if we separated our variables here, we'd get 1 over y dy is equal to, that's a 1 over x dx. This one's more interesting and complicated. Anti-differentiating both sides, we'd get the natural log of the absolute value of y equals the natural log of the absolute value of x and a plus c. We get rid of those natural logs by exponentiating both sides. So we now have the absolute value of y equals, and this gets a little weird here, guys. This is e to a some power. Now, the other way you could write that would be, I guess I should have done that lower, e to the natural log of the absolute value of x, and then multiplied by e to the c. Now, e to the natural log of the absolute value of x, the e and the natural log just drop each other out, and we get absolute value of x, multiplied by e, which of course is a constant, to another constant power just creates another constant that this gets multiplied by. And just as a convention that both your textbook and the AP test writers tend to use, we tend to make that constant a capital C, and we multiply it out in front. And you'd get rid of the absolute value by just taking a plus or minus here on the other side. But since c is an arbitrary constant, it already could be positive or negative. So I would just say that y is equal to c times x. Now, if you think about that, guys, that is a linear function. Whatever c is your slope, which means that your slope can be any constant value. But the y-intercept right there, there is no constant added there, is 0. So how does that fit with our graph? Well, let's just think real quick, guys. If c were equal to 1, your equation would be y equals 1 times x, which would be 1x, and it would fit perfectly right there. If c were something like -1/2, your slope is down 1, right 2, and your line would look like this, and that fits pretty well also. If c were -2 from the origin, your slope would be down 2, right 1. Oh, I forgot to draw that one in there. And it would look something like this. So now you can kind of see why we got this goofy starburst pattern and why every one of those little slope segments was pointed back towards the origin. Kind of cool, I think, anyway. All right, let's do one last one here. This is a complicated one, and if I'm remembering right, this is actually a problem that I stole from an old AP test right here, and I only bring that up because I'm pretty sure we did this at the end of our notes together, you guys, in section 9.1. So I think, not that this matters, this is 2008, the AP test problem number 5, but don't worry about that. Let's dive into it here, guys. Our derivative is y minus 1 over x squared. Okay, the first thing I would look at, anywhere that your denominator is equal to 0, that means that your slope is undefined, which means that it's going to be vertical. So anywhere x is 0, which includes the origin, but also anywhere on the y-axis. Anywhere your x coordinate is 0, that's the first thing we have to watch out for, and there you go. Okay, got that one down. Now, after those 5 points, anywhere the numerator is equal to 0, your slope would be 0, and your segment would be horizontal. Where would the numerator equal 0? Anywhere that y was equal to 1. 1 minus 1 would get you 0 on top. So that one, we'd end up with a slope of 0, and it would be horizontal. So anywhere y is 1, here, 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 not right here, guys, because the verticality trumps the horizontalism. Sure, I'm just making up words now, but there you go. So at all 6 of those spots right there, where y is 1 and x is not 0, we'd end up with a slope of 0. After that, you guys, I'm not really sure there's anything huge to be gained right here, and I think you got to roll up your sleeves and get to work on this one, just kind of one piece at a time. So I'm going to just work on my x-axis, kind of going here and then out to the right that way. So at the point 1, 0, I'd get a -1 on top and a 1 on bottom. That would be a slope of -1. To the right of that, at 2, 0, I'd get -1 on top, 4 on bottom. That would be a -1/4. I think I'm starting to see a pattern here. Let's move to the right. At 3, 0, we'd have a 9 on the bottom, -1 on top. That would be a -1/9. If I moved left now, starting at this point right over here, let's think about that. The only thing different now is that x is going to be negative as we move to the left. Y is still going to be 0. So we'd still get a -1 on top, but on bottom, that -1 squared turns positive again. So right here at the point -1, 0, we're going to get a 1 on the bottom still and a -1 on top. That is still going to be a slope of -1, just like it was right here. So now I think I see something, guys. If those two slopes are the same, I think these two slopes are going to be the same as well. The only difference in these 2 points is that here x was +2, here x was -2, but since your x coordinate gets squared, it doesn't matter whether it was +2 or -2. So yeah, I guess you can maybe steal a little bit of your work right here and kind of go with that. That might be kind of important as we move forward right here. Let me keep going down. I think I'm going to start, let's go to this point right over here, guys. At the point 1, -1. So let me erase that too. Okay, so a 1 for x gives me a 1 on the bottom. -1 minus 1 is a -2 on top. That would be a slope right there of -2. Keep going right here. When x is 2 and y is -1, it'll be -2 over 4. That's a -1/2. Okay, gotcha. And a little bit more to the right now. When x is 3, y is -1. That's a -2 on top and 9 on bottom. That's a -2/9. I think at this point you can kind of start to sense what's going on. But like I said, this one takes kind of a long time here, guys. Where am I? 1, -2 at this point right over here. That's now -3 over 1, so even steeper. And I think I can see a pattern here, guys, as I look at these 3. They're all going to be the same sign, but they're just getting a little bit steeper as they go down because our y coordinate is decreasing each time. So I'm going to kind of eyeball and say, okay, you know what? This one, each one looks a little bit steeper than the one right above it. I'm guessing the opposite thing happens up here high in the first quadrant, but I guess I'll find out. Right here at the point 1, 2. I'm sorry, that would be, no, that is right, 1, 2. So our numerator, 2 minus 1 is going to be 1 over 1. We're going to get a slope of 1 right there. Now I think I'm starting to see a pattern that if we look at these 3 slopes and we read them from left to right, the sign stays the same, but it looks like they are getting less steep as we move out to the right. I think that same thing's going to happen. Let's talk about the point 2, 2. That would give me a 1 on top and a 4 on bottom. So there's a slope of 1/4. And I think this next one, the point 3, 2, is going to get me 1 on top and a 9 on bottom. That's going to be 1/9, even more shallow. And then let's take advantage of the lesson that we learned here and here. The only difference between these 2 points is that their x coordinates were opposites, but that doesn't matter since we're squaring the x. So whatever slope I got right here, you guys, I think we're going to get the exact same slope here, and likewise with these 2, and likewise with these 2. So it's a difficult one to verbalize and explain what's going on, but I do think there's some patterns that we can steal here. So if that slope was 1, that'll be 1. Oh, wait a minute. I went too far in my erasing there. Shoot. All right, I guess I better keep that there. That slope is going to be 1. This slope, I think, was 1/4, if I'm not mistaken. This would be the same. And then that 1/9 right here, we'd copy right over there. Okay, so now I'm just kind of mimicking here what I'm seeing from the right side over to the left. These graphs do not need to be perfect, everybody. They just need to be relatively accurate, and that should give us a decent sense for what's going on with those slope fields. This one, ooh, I don't have it in front of me here, guys. Sorry, what the solution to that Diffie Q was. I'm going to trust that that would fit in there pretty well. Okay, that's the video I'm going to make now for the first half of section 9.3 on slope fields. I'll come back and make another one in a minute when we talk about a numerical method for approximating the solution to a differential equation, and that's going to be called Euler's method. But that'll be our next video coming up. Good luck, everybody.